What is FMEA? It's a proactive process to identify, assess, and then remove or mitigate risks associated with a product design, process, or monitoring and system response. We're going to focus on process FMEA in this presentation. There are, by the way, other FMEAs that can be done, for example, for supply chain, because the supply chain is so critical to continuity of operations, and any interruption in the supply chain can shut down an entire factory. So FMEA can even be done with supply chain as well. That's another potential application for it. FMEA is part of AQP. It's part of advanced quality planning, and AQP is a set of cross-functional activities, and I stress cross-functional, that delivers a quality plan for alignment of a process, product, or service with customer requirements, and it's documented as a quality record. The handout has some additional information in the notes pages. There's a free reference on production part approval process from Cooper Industries, and the link to that is given. There's also a reference for advanced quality planning by D.H. Stamatis, available from Productivity Press. That's an excellent reference. If you're not a member of the Automotive Industry Action Group, their manuals are extremely expensive, I think on the order of $150. They're very good, by the way. I recommend them very highly, and I've purchased them myself. But if you're looking for something less expensive, the Stamatis book on advanced quality planning also is highly recommended. Design of new products, ISO 9001, Clause 8.3, design and development, development of new processes, process or product changes that may affect safety or regulatory compliance, transfer of tooling to new processes or plants. Roles in AQP or APQP, the item on the top is quality function deployment, also known as the House of Quality, where we communicate our requirements to our suppliers, our customers communicate their requirements to us, and we determine how to fill those requirements. The quality function deployment provides inputs to the design FMEA. The design FMEA gives us critical and significant characteristics, and those must then be addressed by the process FMEA, which is the focus of this presentation. It shows which activities require controls, and that leads us to the control plan, which in turn helps define the gauges. Error-proofing device Poka-Yoke is error-proofing, and statistical process control. IATF 16949 and AIAG's Advanced Product Quality Planning Manual provide information on control plans, which are, by the way, required by IATF 16949. They're probably a good idea for ISO 9001 users as well. There's a lot of material in IATF 16949 that is not found in ISO 9001, but it can be used to enhance any ISO 9001 quality system. So that's something else I recommend, is to look into IATF 16949 and see what portions could be added on to an ISO 9001 system. Also, the Stamatis reference also provides information on control plans, and I also cited the link to the downloadable one from Cooper Industries if you want to know more about control plans. ISO 9001 Clause 6.1 requires actions to address risks and opportunities. FMEA anticipates proactively risks associated with product or process failure modes. Now, I say proactively because after the failure has occurred, we have a corrective and preventive action process, which also is, of course, mandatory. We have to correct our quality problems audit findings, customer complaints, and so on. But CAPA is usually invoked after the fact, after something goes wrong. FMEA tries to identify and prevent it before it goes wrong. We look, how can this go wrong? What controls can we implement to prevent it? IATF 16949 requires design risk analysis, that's design FMEA, and the manufacturing process design output requires a process FMEA and control plan. Additional role, FMEA can be leveraged to reduce the cost of poor quality, so there's some monetary payback here. This is from an AIAG FMEA webinar, I think from the Automotive Industry Action Group from last year. So it can reduce the cost of poor quality, which of course delivers bottom line results. Any money we save flows directly to the bottom line. I believe that dates back to Benjamin Franklin when he said, well, the most famous version of the statement is a penny saved is a penny earned. What that means is, let's say it takes $10 of additional sales to bring in $1 of additional profit. Well, if we save $1, that's the same thing, and we don't have to have the additional sales. So this is extremely important. FMEAs can be developed for design, process FMEA, monitoring, and system response. That's also in the AIAG VDA FMEA manual. Quality management system, you can actually do an FMEA on your quality management system. And I mentioned the supply chain as well. And there's actually an IATF 16949 clause. All of this is cited in the handout notes, by the way. Has a clause on contingency plan that addresses continuity of supply, which suggests the desirability of the supply chain FMEA. We had a incident actually in Pennsylvania. The Susquehanna River is not exactly our friend, at least not during heavy rainstorms. Of course, a flood in 1972 essentially destroyed the city of Wilkes-Barre. I mean, it didn't destroy the city, but it caused so much damage that it took years to rebuild. More recently, we had a flood downstream, I think somewhere around Bloomsburg, that affected some plants in the automotive supply chain. I think it was. I'm pretty sure it was downstream for us somewhere. And that would be another example of supply chain interruption. So we might want to do FMEA for supply chain as well. There were also some earthquakes over in Japan a while ago, which I think interrupted semiconductor industry supplies, which is yet another example of wanting to have FMEA for supply chain. Okay, the AIAG VDA process is now qualitative rather than quantitative. If you've been using previous versions of FMEA, you will hopefully like the changes. This is a major advance on previous versions. First of all, it's qualitative rather than quantitative. We previously had to try to quantify the occurrence rating, which previously assumed knowledge of the specific likelihood of occurrence, which is possible to determine if you have process capability data. You can estimate the nonconforming fraction from a process, although that doesn't cover special or assignable causes, which can increase the nonconforming fraction. But quite frequently, that information was simply not available. So the new occurrence rating is based on the nature of the controls used to prevent the failure mode, as opposed to having to estimate the probability that something will go wrong. Focuses on single point failure analysis, should be cross-functional in nature. Scope includes only technical risks, not risks related to finance or strategy. So, for example, a risk associated with technological change making your product line entirely obsolete is not addressed by FMEA, only the technical risks of the process. So separate activities are required to address strategic risks. As one example, they're talking about a means of getting electricity from moisture in the air. There's apparently can generate some pretty weak electrical currents by doing that, and they're saying, oh, that's irrelevant. You can barely light a single LED bulb with that. Well, that might be true today. Maybe 5 or 10 years down the line, though, that could pose serious challenges for other forms of energy generation. So that's a strategic risk, but which is not covered by FMEA. The FMEA addresses only what we're doing in our current process. Foundation or generic or master FMEAs are based on past experience and serve as starting points for new FMEAs, which means it can save work. Family FMEAs or foundation FMEAs for specific product families, and this is related to group technology in which a similar set of parts can be manufactured by the same tooling sequence or work cell. So if you simply changing the tooling in the work cell can make different parts, that would be part of a part family, and the FMEA, that saves a lot of work with the FMEA because you don't need a separate FMEA for each part. FMEA should be updated or created for new or changed designs and processes. That management of change is worth remembering. It's originally from process safety from the chemical process industry, which says any time we change a process, it can create a potential hazard, and a change can involve a startup. For example, I get the American Institute of Chemical Engineers magazine, and they have these safety case studies. There was one where they emptied an oil tank, purged the lines with steam, and then apparently some of the steam condensed in the pipes. They put hot oil in, which expanded the water and blew the tank open, caused some serious damage. But that's an example of a change. Simply shutting down and starting up can create a hazard where none existed during the original process. Any change in the process can create a potential hazard. Similarly, anytime you change your process, say bring in a new material, a slightly different material, slightly different way of doing the job, that can have unforeseen consequences. So it's important to update accordingly to account for that. Any change in the cause and effect diagram category creates a risk. New operator, new machine, new supplier, or change in the raw materials. There was a case in which, I think also from Chemical Engineering Progress, as I remember, where they were using a water supply for a process, and then they changed over to the municipal water supply, thinking, well, water is water. The problem is municipal water has trace chlorine in it to kill off bacteria. That's how we assure the safety of our drinking water. But chlorinated water is not good for certain types of piping, and they actually had a serious problem because now they had trace chlorine in the water where they had none before, and that was due to a change in the raw materials and something most people wouldn't pay attention to. New procedure, which is why we have a review process for work instruction changes. New environment, such as change in temperature, humidity, and other considerations. New or different gauges. And there's some additional notes in the handout where we don't have time to go over them here, but they are available in the handout notes, some examples of this. For the process FMEA, there are 7 steps, and this is from the AAAG VDA manual. which is an extremely good reference. Planning and preparation, structure analysis, function analysis, failure analysis, risk analysis. By the way, they no longer have the risk priority number, which had some drawbacks. Now they have an action priority matrix, which makes a lot more sense. And apparently that manual is the only source of the action priority matrix, so it is necessary to purchase that manual to have access to it. But it is a major advance over the previous approaches. Optimization, actions to remove or mitigate risks, documentation, the FMEA becomes a quality record and part of organizational knowledge. Another change where it talks about identification of failure causes, that was previously known as the failure mechanism. So they just changed a little wording on that, but it's really the same thing. Planning deliverables, scope, baseline FMEA, FMEA headers. These are basically the headers of the FMEA, like who's responsible, what product line, what factory. It's essentially routine information. I'm not going to get into the details of that. Structure analysis. And structure analysis is pretty much means the process flow chart. How is the process structured? What are the process steps? And what are the process elements? And this is consistent with the process flow chart, which we're probably already using because of the process approach of ISO 9001 and IATF 16949. The process steps later become focus elements for identification of failure modes, and the process elements are sources of failure causes, which were again known as failure mechanisms. Okay, so structure analysis, where it says structure tree, that's simply really what it means is a process flow chart. I can't see any practical differences between the structure tree and a process flow chart, but basically it shows how the process is structured. Function analysis, that simply means what is each process step and process element supposed to do to achieve the process objective. Failure analysis, that's pretty much self-explanatory, and that includes the failure mode, the failure effect, and the failure cause. And basically the negative of a function, namely the objective not achieved, is the failure mode of the process step. That is, what was the process step supposed to do that it didn't do? What is the failure effect is the consequence. What is the consequence for quality? Like, well, the final assembly doesn't work. Failure cause is the process element that causes the failure mode, previously known as the failure mechanism. Risk analysis, identification of prevention and detection controls, severity, occurrence, and detection ratings give us an action priority as opposed to a risk priority number. Optimization deliverables, actions to remove or mitigate risk. Basically, what do we do to correct and improve the situation? Documentation, it becomes a quality record, and deployment of lessons learned. That last part can't be overemphasized, because suppose we have a similar process, not an identical process, but a similar one, maybe they can benefit from the knowledge as well. Planning, define the scope of the FMEA, which products and processes are to be included and excluded, how much control do we have over the design of external products. Processes can go beyond product realization, which is the traditional focus of FMEA, to encompass receiving, storage, transportation, and anything else that might affect quality. It can also apply to services, which would include certain practices in the hospitals, anything done to a patient, like connecting an intravenous line, That's a process, and the severity mode of the failure is 10 because it puts human life at risk, and they can also have controls, prevention and detection controls there, so this can carry over if you're in some sort of service activity rather than manufacturing. This is also usable in many service industries as well. Safety is within the scope of process failure mode effect analysis. There are actually a separate category for occupational health and safety in the severity ratings. Usually anything relating to occupational health and safety is going to be a 9 or 10 severity on the 1 to 10 scale, with 10 being the most serious possible. In general, any time you see the words new or changed, that shows that FMEA must be performed or updated, because any change is a source of risk. Generate a project plan. If design is involved, the design FMEA should be part of the plan. Identify the baseline PFMEA, which is the previously mentioned foundation PFMEA, especially if we have a product family and group technology. That can be helpful because group technology applies to all the parts in the product family, so that all that must be added are the components specific to the new or changed product. Fill out the header, which is probably going to be unique to your organization and pretty much routine. So the next step is structure analysis. Now we'll get into the actual preparation of the FMEA. It's a disciplined process for identification of activities that require risk assessment, and the deliverable is a structure tree with the process steps, which pretty much come from the process flow chart, and the process elements, which are not necessarily part of the process flow chart, that affect the process steps. So essentially, structure analysis is very similar to the process flow diagram, but we're also going to add the process elements or factors that affect the process steps. Another way of saying this is we're simply identifying the operation of the process and the cause and effect diagram factors that might affect the operation. There's actually a very strong similarity between this and the cause and effect diagram with regard to the process elements. The process item is the overall process and its objective. Basically, what's the process supposed to accomplish? This is the highest level item in the structure tree. What is the process supposed to accomplish? What is its deliverable? The process steps are the individual operations of the process. This is the focus of the analysis, and the failure chain affects the process steps. The process elements are factors that can affect the outcome of the process. The manual cites manpower, machine, material, and environment. We could also consider method and measurement, which are the other cause and effect diagram categories as well. Here's an example. The best way to do this is with an example. This is drawn from Shigeo Shingo's book on zero quality control. And the context is, by the way, Shingo is not doing FMEAs. He's simply talking about the problem, the failure mode, and the error proofing or automation measures that are put in place to prevent the failure mode, but he isn't doing FMEA. I adapted this as an FMEA example. Basically, the worker is supposed to check the bolt torque with a torque wrench and sometimes forgot to do so. Failure to do so depended on worker vigilance. Now, as soon as we see worker vigilance in any Shigeo Shingo case study, we know that errors and omissions are going to happen because worker vigilance simply, it doesn't make it impossible, and the FMEA occurrence ratings echo what Shigeo Shingo was saying, because what they call behavioral controls or administrative controls, you don't get a very good occurrence rating from something that relies on worker vigilance. The principle isn't that workers are careless or they don't care or they aren't vigilant. The principle is if it's possible to do the job wrong and you do it enough times, eventually you're going to do it wrong. Okay, in any event, this is the process in the Shigeo Shingo example where we bring in parts, car seat and back from a previous process, bolt them together with an impact wrench, check the bolt torque with the torque wrench, which is the focus of the Shigeo Shingo example, and then send the assembly to the next station. This is a very simple example we can use to illustrate FMEA. Now I turn this into a structure analysis based on the AIAG FMEA manual to simply illustrate what the FMEA manual wants us to do. The process item is the bolt installation for the car seat, and that is what the process is supposed to accomplish. It's supposed to bolt the back of the car seat to the horizontal part of the car seat. The process steps, and those were drawn directly from the flow chart on the previous page. Place the bolt, tighten it with an impact wrench, and check the torque with a torque wrench. Now note the similarity to a cause and effect diagram, because at the far right we have the process work elements, which are the potential failure causes, like tighten with impact wrench. We have generically manpower, machine, material, environment, and we know specifically that that step is going to depend on the impact wrench. That's the tool that's being used. Similarly for the torque, checking the torque, the tool used is the torque wrench. So we've identified that as a process work element. We enter this in the PFMEA spreadsheet. That's one of the handouts, and I did it to show how some of the elements of this case study would appear in an actual PFMEA following the Automotive Industry Action Group VDA format. And the highlighted row is for the Shingo example in particular. So we see, for example, the process work element is the worker, the bolt, and the torque wrench for checking the torque. Function analysis identifies what each process step is supposed to do. That is, it's similar. It builds on the structure analysis. The structure analysis shows what the process steps are. The function analysis tells us what each process step is supposed to accomplish. In this case, assemble bolt into the seat. The negative of the process item is the failure effect, such as bolt not installed or torque not within specification. The failure effect is what happens that shouldn't. In other words, the bolt is either not installed or is installed with the incorrect torque. The failure mode is how it happens. In this case, the failure mode appears to be the worker sometimes forgets to check the torque. The failure cause is why it happens, and we're going to see that the worker is inattentive or careless is not an acceptable failure cause in terms of actually solving the problem. The failure cause, again, was known previously as the failure mechanism. The function of the process step is what is supposed to happen to the product feature. Place the bolt, tighten the bolt, check the torque. The negative is the failure mode, how the failure occurs. Well, if the function is place the bolt, then the failure mode is the bolt not placed. Tighten bolt is the function. Bolt not tightened to specification is the failure mode. and so on. The function of the work element is what the work element does to realize the process step. So in this case, the worker checks the bolt torque with the torque wrench. The negative is the failure cause, the failure mechanism. Note it says Y, which ties in with the 5Y analysis. We say, okay, why wasn't the torque checked? The worker forgets, and we might want to ask why that happened. The answer is not the worker is careless, but it's possible to forget. The actual failure cause is it's possible to forget, and if it's possible, sooner or later it will happen. Another possible failure cause is the torque wrench isn't set to the correct torque. Another perspective treats the process step or process function as the focus element, asks how this higher level function is realized by the lower level function process work element. The function of the process step is what happens to the product. The failure mode is what doesn't happen that should have happened. The process work element is how it happens. The failure cause is why it doesn't happen. And the best way to illustrate this, this often becomes much simpler if one uses an example. The process function is tighten the bolt to specification. This is what is supposed to happen. The process elements are how the process happens, how the process function happens. The failure cause is why the process function was not realized. Product and process characteristics. Product characteristics are measurable or otherwise appraisable aspects of the product. But the key point, the key difference between these, we're going to need these when we get to the risk analysis, because the product characteristics are usually measurable or appraisable only after realization of the product, such as, for example, what torque was the bolt tightened to? Well, we have to tighten the bolt with the impact wrench before we can measure it with the torque wrench and find out. And that means they're measurable by detection controls, and detection controls are not really as good as prevention controls. They're extremely important, but the prevention controls are more important. The process characteristics are things we can measure while the product is being realized, and that's where we have prevention controls. Suppose a hole is supposed to be drilled to a certain depth, and as the drill press advances the drill into the part, the depth to which the drill penetrates the part can be measured at any time, so that would be a process characteristic. And the prevention control would be something to control the distance to which the drill penetrates, whereas suppose we measure the depth of the hole afterwards, that would be a detection control and therefore a product characteristic. How this might look in the PFMEA spreadsheet, and again we're focusing on the yellow highlighted lines. What happens? We're assembling the bolt into the seat. For the check, how it happens, we're checking it with the torque wrench, and the work element is the worker checks the torque with the torque wrench, and that's the source of the failure cause. If the worker forgets to check the torque, or if the torque wrench is set to the wrong torque, then we're going to have a failure cause. A parameter diagram organizes information related to the process and its requirements. It includes the bill of materials, the inputs, bill of materials and consumables, intended outputs, process noise factors that can become failure causes, product and process characteristics, and affected or changed process characteristics. What does the process modify or alter? In this case, we're altering the tightness of the bolt as measured with a torque wrench. The Stamatis reference adds at the control plan stage that the control factor supports the process characteristic in terms of being a potential source of noise or variation. So the control plan is going to tie in very closely with the FMEA's parameter diagram, and Stamatis gives 8 possible sources of noise or variation. This goes a little beyond what the AAAG VDA reference gives us. The next step is failure analysis. We've seen where the failure causes might come from. Now we have to identify the failure causes, failure modes, and failure effects. The failure effect is what happens that shouldn't happen or doesn't happen that should. The failure mode is the focus element. That is, the focus element means simply the starting point of the assessment. Something I'm hoping to do here, by the way, is to put some of the terminology in the AAG FMEA manual and make it somewhat more understandable in terms of an actual example and how it's actually supposed to be used. So when they say focus element, it simply means this is the starting point of the assessment. We don't start with the failure effect or the failure cause. We start with the failure mode. In this case, the worker forgets to check the torque. That's the starting point. From there, we go to the failure effect. Well, we don't know what the torque is, so we effectively haven't measured a vital process characteristic. And then we also look for the failure cause. Well, why might the worker forget to check the torque, which is the failure mechanism? Consider failure effects that could affect quality, which is the traditional focus of FMEA, continuity of operations, also occupational health and safety. An OH&S risk can have a rating of no less than 8 according to the AAAG VDA manual, and previously an OH&S risk couldn't have a severity rating of less than 9, but I'm assuming that chronic health or safety risk relates to one that will give warning before it results in permanent harm or impairment. For example, repetitive motion injury that makes itself known to the worker before serious harm can happen. If it can cause greater harm, my inclination, I'm not giving engineering advice here, but my inclination from a safety perspective is that if it's capable of causing greater harm, my inclination would be to rate it no less than a 9. And an acute risk is defined as a 10. That's something that can cause immediate injury without any warning whatsoever. This is all given, though, in the AAAG VDA FMEA manual where they have severity ratings. Okay, so we can have quality, continuity of operations, and occupational health and safety. The failure mode, how it happens or doesn't happen, is the focus element, which means simply it's the starting point. It's in the middle of the failure chain between the effect and the cause. Start with identification of the failure mode. How does the process step fail to meet the requirements? The worker forgets to check the torque. Determine what happens, which is the consequence. Determine why it happens, which is the failure cause. The failure mode is the focus element or starting point. How it fails, the failure mode and the consequence of that is the failure effect. How it fails is the failure mode, and why it happens is the failure cause. That should be it rather than if. I just happen to notice that. How it fails is the failure mode. Why it happens is the failure cause. Failure mode, the bolt's torque is not checked properly. That could also be because of the torque wrench not being calibrated properly, although the Shigeo Shingo example focused on the worker forgetting. But that's the starting point. The focus element or starting point is that the bolt's torque is not checked properly. The failure effect is the bolt is not tightened to specification, or for practical purposes might as well not be tightened to specification because we essentially haven't performed a required test. By the IATF 16949 also is very strong on things like traceability of information relating to the product, and also making sure that all of the required tests and quality checks have been performed. So basically, if the worker isn't checking the torque, or if the torque wrench is out of calibration, we're shipping car seats and we don't know what tightness, what torque the bolt has been tightened to, so we could have a real problem on our hands. Failure causes, worker forgets to make the check, that's under manpower. The torque wrench is not properly set or properly calibrated, which is a measurement issue, and the AIAG FMEA manual doesn't include measurement, which is a cause and effect diagram category up front, but this is a good reason to consider it. How do we know the torque wrench is properly set and properly calibrated? There's a tie-in here with corrective and preventive action. This Automotive Industry Action Group manual also is an excellent reference, effective problem solving. It's similar, by the way, to 8D, the 8 disciplines approach, which is another extremely effective corrective and preventive action process. Both of them work extremely well, probably the best ones available. In any event, there's 3 root causes for a problem. The occurrence root cause is why it happened. Now that's the FMEA failure cause. That's the occurrence root cause. The escape root cause is how it got to the next internal or external customer, assuming it did, assuming it wasn't caught before it got out of the workstation. Well, that could be failure of the detection control that's designed to prevent escape of poor quality. The systemic root cause is why the system or planning process didn't identify these issues ahead of time. So if CAPA finds the occurrence root cause, we should ask why FMEA didn't identify it before it actually became a problem. Here's how it looks in the FMEA document. That double-headed arrow shows that the failure mode is the focus element or starting point. So we're starting in the center of that. We're not starting on the left. We're not working left to right. We're starting in the center. The failure mode is torque not checked. The failure effect is the bolt is not assembled with a known torque. And the failure cause is worker forgets. I also have on top, which is not it's not in the Shigeo Shingo example, bolt not tightened to correct torque. The consequence of that would be bolt not assembled with correct torque, and the failure cause of that would be the impact wrench not set for correct torque. Risk analysis, we're assessing the risk associated with the failure mode and identify controls associated with the underlying failure causes. Prevention controls reduce the occurrence rating, and by the way, lower is always better. It's on a 1 to 10 scale. 1 is best, 10 is worst in all cases. It mitigates or disables the failure cause. Detection controls improve the detection rating by detecting the problem before the product advances process. There's a connection there between prevention and detection controls in the FMEA and also the process and product characteristics. Remember, I have a whole slide on process and product characteristics. The process characteristic is something we can measure while the process is taking place, and it's usually subject to a prevention control which influences the occurrence rating. It's something that gives us feedback as the process is happening. I remember from semiconductor, we were supposed to etch a certain distance through a dielectric layer with either hydrofluoric acid or in some cases plasma, and they had an endpoint detector that actually showed when the dielectric had been penetrated by the etchant, and I think some additional time was added to make sure it was through completely. But that's an example of a feedback process control. It measures what the process is doing while it's doing it, and it prevents the problem from happening. The product characteristic is measurable or appraisable after the product has been created. Detection controls can detect the poor quality, but we've already made the poor quality. Now, something else they can do, it's called JIDOKA or automation. It can also stop the process before it continues to make poor quality and possibly creates a lot of scrap. Maybe we'll lose one part of scrap, but if the detection control finds that, it can shut the tool down and alert the operator so we don't make more. Prevention controls include source inspections and error proofing. By the way, Shigeo Shingo's book, Zero Quality Control, is an outstanding reference for this, and I believe Productivity Press's Shop Floor series has a book based on Shigeo's book that talks about exactly how this works. Now, there was the Ford Motor Company says, don't take it, don't make it, don't pass it along, with it relating to poor quality. So vertical source inspection assures incoming materials are good. In other words, don't take poor quality. If the incoming materials and parts are defective, we aren't going to do anything with them. We're not going to take poor quality, because if we take poor quality in, we're going to get poor quality out. Horizontal source inspection is simple language for in-process control that prevents errors from becoming defects, and that's how we avoid making the poor quality. Self-check systems catch the poor quality before it can get to the next process. Don't pass it along. So when our customer process does the vertical source inspection, we're not going to send them any poor quality that they don't have to take. So this is from Shigeo Shingo's book, which supports FMEA very strongly. Correspondence between PFMEA and error proofing. Prevention controls usually act on process characteristics. Detection controls usually act on product characteristics. In the bolt tightening example, worker vigilance is an administrative control and a highly inadequate one. Next, define the severity, occurrence, and detection ratings. And the AIAG VDA references tables are significant advances over the ones that were used 20 years ago. And hopefully, as a user of FMEA, you will like these a lot better. Failure effect severities, consider internal failure, external failure, impact on the end user, occupational health and safety. 9 to 10 is high. 10, risk of acute injury to a worker or product safety. In other words, if the defect in the product can cause death or injury to the end user, or if the process itself can cause death or injury to a worker, that gets the worst possible rating. Remember, 10 is the most serious. 9, non-compliance with regulatory requirements. And by the way, there can also be a tie-in here with ISO 45001, the Occupational Health and Safety Management System. Moderately high for occupational health and safety, say chronic health or safety is 8. And again, I'm assuming that that's something that's going to make itself known before it can cause actual harm. My personal inclination would be if it can cause harm to the worker without advance warning, then that has to be a 9 or a 10, because protection of the workers has to come first. Now also we're getting into continuity of operations. Notice a line shutdown can get an 8, but because it doesn't endanger human life or safety or noncompliance with a regulatory requirement, it can't be rated 9 or 10, but it can be rated as an 8. From a financial perspective, we're talking about just money as opposed to safety. 8 is essentially the worst that can happen to us. Similarly, the product doesn't work, like the car simply doesn't start and we can't go anywhere with it. Well, that doesn't endanger safety, because if we can't go anywhere, we can't go out on the road and get in an accident as opposed to a brake failure, but essentially the product's unusable. 4 to 6, moderately low, 2 to 3, low, and 1, very low, nobody is likely to care. I've also put in the handout. We don't have time to get into it in this presentation. There's a correspondence with the Army Risk Management DD 2977 Deliberate Risk Assessment Worksheet, which could conceivably be used as an alternative to FMEA if in a situation that isn't very complicated and where FMEA isn't required, for example, by IATF 16949. But that's really a separate issue. I have given the correspondence between these ratings and the Army Risk Management Process severity ratings. The occurrence ratings, 10, essentially no prevention controls. Now remember, I said in the Shigeo Shingo case study, relies on worker vigilance, and as soon as he says that, we know there was trouble happening because worker vigilance is not an adequate prevention control. Well, here's where it is on the occurrence rating according to the AAAG FMEA manual. Controls are behavioral, rely on vigilance and compliance. We can also have better behavioral controls, can get a 6 to 7, 4 to 5. Actually, low and very low controls or best practices, technical or behavioral. I'm trying to think of a behavioral control that could actually get us down to a 3. Or maybe in certain cost accounting systems where it's done manually, it requires on the vigilance of the accountant, but if the debits don't balance the credits, the accountant will notice that immediately and realize that there's a mistake. That could conceivably get us down to a 3. Extremely low controls must be technical and must disable the failure cause totally. Now what's significant about that is if we get a 1 occurrence rating, we get an action priority rating of low, and this is the first time I've seen a low action priority for a 10 severity rating. The way the action priority matrix is structured, if we have a 1 occurrence rating, we get a low action priority regardless of the severity and detection ratings, and that's probably because if it can't happen, that is, can't as is in probability 0 as opposed to almost 0, we don't have to worry about it. And that will be illustrated in some of these examples where we can get an extremely low occurrence rating. No, this is a change I think everybody will like, because instead of having to estimate the probability of occurrence, such as percentages or defects per million opportunities, which was the case in some of the previous manuals, this simply wasn't practical, and when people had to do FMEAs, they sort of had to guess, like, how often does this happen? Well, we'll put this in for the occurrence rating. Nobody was really happy with it, and I think a lot of people didn't like to do FMEAs for that reason, among others. Well, in this case, you know what kind of prevention controls you have in place, so at this point we can get a much better picture of our occurrence rating. Ability to detect very low failure mode is hard or impossible to detect. I remember Henry Ford complained that defects in metal castings were extremely hard to detect, well, at least with the technology they had 100 years ago. Now I think they have non-destructive methods that can detect them. But anyway, that's why he preferred not to cast parts and then machine them. He preferred to make smaller parts and weld them together to get the final assembly. Then he didn't have to worry about that. Low human or automated inspections that should, I believe the manual actually uses the word should. Should is not a very reassuring word when it comes to detecting a problem, and it improves from there. Now, when we get down to automated, to get a 2 to 4 high-level detection, we have to have automated methods. 1 very high, the problem can't be generated or detection is 100% certain. Now notice in this case, anything that relies on worker vigilance can't get a detection rating of better than 6. The manual says machine-based is required for 5 or lower. Correspondence with the Army risk management process, which encompasses detection and occurrence put together. These are the ratings that the Army uses. So there's a tie-in there. Okay, recall from effective problem solving 3 root causes for the problem. The occurrence root cause is likely to be the failure cause. The escape cause relates to detection. And the systemic root cause is why we didn't identify it ahead of time. The new AAAG FMEA manual uses an action priority matrix instead of the risk priority number. I believe there's in the handout cites Donald Wheeler problems with risk priority numbers from back in 2011. He pointed out, among other things, that the risk priority number is the product of 3 ordinal numbers. So we have one with a severity of 10, which means it can kill somebody, with a risk priority number of 200, and another one with severity of 4, which can only annoy the customer. On the other hand, it's going to happen more frequently because there's really no detection control and there's a moderate occurrence rating. So we have 2 things with a risk priority number, one of which can annoy customers, can annoy a lot of customers, and the other one which can kill a few customers, and obviously the one with severity of 10 requires a lot more attention than the one with severity of 4. Now they did have something called the legal zone. Anything with a 9 or 10 requires attention regardless of the RPN. But I think the action priority matrix does a better job with this. The action priority matrix gives highest consideration to the severity, followed by occurrence, and finally detection. Obviously, it's better to prevent the failure from occurring at all than to detect it after the fact. Action priorities, there's only 3 of them, high, medium, or low. The only concern I have about this is it's possible to get a low rating with a 9 or 10 severity as long as the occurrence rating is no more than 3 and the detection rating is no more than 4. It means generation and escape of the failure mode is highly unlikely but not totally impossible. My personal opinion is that if escape of a 10 severity failure mode is possible, I don't think it should have a low rating. but that's just my opinion of it. The Army's risk management process does not allow a risk rating of lower than medium for a severity rating of catastrophic, even if the probability is rated as unlikely. So you can see here catastrophic would be severity of 9 or 10. Unlikely, possible occurrences, but improbable, that can't be rated lower than medium. Okay, and then the event, return to the bolt installation example, consider the failure mode bolt not tightened to specification. Severity is 7, as we may have to have 100% recheck later to find non-conforming work. In other words, somebody's going to have to go and check all those car seats with a torque wrench to make sure they're bolted to the correct torque. We're assuming an occurrence rating of 5 because the original example doesn't have enough detail to identify the prevention control, if any. Detection, it says the check with the torque wrench should find bolts not tightened to specification. Again, should is not a very reassuring word. The action priority matrix delivers an action priority of high for severity 7, occurrence 5, and detection 8. Here's how it would be entered in the spreadsheet. Again, okay, we have risk analysis, prevention control. I'm assuming work instruction, no formal control. Detection relies on worker vigilance, and coupled with a severity of 7, we have an action priority of high. Optimization means selection and verification of actions to reduce risk. Shigeo says they installed the detection control to tell the worker he forgot to use the torque wrench. The preferred order of optimization is to eliminate the failure effect, reduce the occurrence rating, and finally reduce the detection rating. Remember, occurrence equals 1 will actually give us a low action priority even for 10 severity and 10 detection, because occurrence of 1 means it can't happen. We have to ensure that we try the actions and verify their effectiveness. When the action's implemented, reassess the ratings and retain the original ratings for comparison. Return to the car seat example. A new detection control was added. Use of the impact wrench started a timer. If the worker didn't use the torque wrench within the given time, and we're probably dealing with standard work there, the entire process step probably had a time assigned to it, and that included using the torque wrench to check the torque. Well, if that didn't happen, then a buzzer sounded, and also apparently they had some sort of assembly line which stopped because the car seat couldn't then leave the workstation. That's an example. Don't pass it along. If you have poor quality or questionable quality, don't pass it along. This reduces the detection rating to 5 for machine-based detection with audible or visual warning. So we get a new action priority. Instead of high, it's now medium. And that's reflected in the FMEA spreadsheet. Detection, buzzer confirms use of torque wrench. We still have a severity of 7, occurrence of 5, but detection is reduced to 5. And from that, we get a action priority of medium. Documentation, the PFMEA is a quality record. There's additional information on the role of documentation. It's not a once-and-done activity, but should be redone or reassessed in response to anything changed or new. Remember, anytime you see the words changed or new, that should be a red flag. We have to look at this again and make sure that whatever we're changing or whatever is new is not going to cause a problem. Don't forget to deploy lessons learned related to related process. I'm going to go over a couple more examples to show how, hopefully reinforce how this works so you get a good picture of how this new PFMEA process works. This is an occupational health and safety example. This is from a book written almost 100 years, an article written 100 years ago, How Henry Ford Saves Men and Money, from National Safety News. Here's the structure tree: sew fabric for a car seat. The process steps: put fabric into the sewing machine, operate the sewing machine. Pretty straightforward. Failure mode, starting point, how it happens: worker puts hand under needle while handling the fabric, and according to the reference, this happens 3 or 4 times a day. Obviously, telling people to be careful is not an effective control. And remember, any kind of puncture wound back then was a lot more dangerous than it is today because they didn't have antibiotics, and the tetanus vaccine had yet to be invented. The failure effect, okay, remember the failure mode is the focus element or starting point. That's what happens, what goes wrong, how it happens. The consequence: worker suffers a dangerous puncture wound, severity of 10. Failure cause: worker is careless. As soon as that's not a valid failure cause in terms of solving the problem. Now, when we see machine is unsafe, that might be a better place to look. Risk analysis: severity is 10, can cause immediate and serious injury. Occurrence is 9 because we have an administrative control that tells people to be careful. Detection 8, relies on vigilance. So the action priority is high regardless of the detection rating. Optimization step. This is a public domain picture from the How Henry Ford Saves Men and Money. They put a guard which costs 75 cents, and that might be more like $10 today. We're talking 75 cents, and the money of 1920 was a lot of money. In any event, that guard allows the work, the fabric, to be slid under that needle, but the worker's finger can't go under the needle, which makes the accident physically impossible. Now, it doesn't eliminate the failure effect, but it disables the failure mode. So the severity is still 10, but the occurrence rating is now 1 because it's physically impossible. And regardless of the detection rating, the occurrence rating of 1 reduces the action priority to low. Don't forget to verify the effectiveness of the new control. The Resnick reference says it was now impossible to put your finger under the needle. Document the improvement and share the information with similar processes that might benefit from it. So every process owner with a tool with any kind of exposed moving part should look at this similarly. Now, we take that for granted today. Machine guarding taken for granted today. That was not the case 100 years ago. Assume the owner of the process sees what was done with the sewing machines. This is a punch press. This is the structure analysis of a punch press. It's also drawn from the Resnick How Henry Ford Saves Men and Money, written in 1920. Now, again, they didn't have FMEA in those days. I'm just adapting this to an FMEA example. Failure mode: worker puts hand in the punch press while the press is in operation. Failure effect: again, 10 severity. People lost fingers and hands in that manner, apparently thousands a year throughout the country. Failure cause: again, we're obviously heading towards machine is unsafe as opposed to workers are careless. Severity is 10, obviously, can cause immediate and serious injury. Occurrence 8, behavioral, controls that rely on people to be careful. Detection, they had a procedure called tap signaling, where one press operator warns the other when he's about to close the press. Yeah, it might work 999 times out of 1,000, but all you have to do is get it wrong once, and somebody's going to lose a hand or fingers as a result. So the action priority is high regardless of the detection rating. So what they did was they had an engineering control. Each worker must press 2 buttons, neither of which is close to the moving parts, to close the press. Now it's physically impossible to have a hand in the press when it closes. This actually is similar to lockout, tagout, where if you have 2 people working on a piece of dangerous machinery, each one locks it out, so neither one can start it up until both of them are done with the work. In this case, it's essentially locked out until both workers press 2 buttons apiece, which means they're absolutely sure nobody's hand is near the moving parts. Again, doesn't eliminate the failure effect. If it happens, somebody's going to lose a finger or a hand, so the severity is still 10, but occurrence is equal to 1 because it's physically impossible for it to happen. So the new action priority is low. This one is a manufacturing example going from occupational health and safety back to manufacturing. Drill holes in the part known as a capsule. This is again from Shigeo Shingo's book. Now again, Shigeo Shingo isn't doing FMEA. I'm adapting his example to show how FMEA would handle it. Spot face and drill 4 holes in the part seems pretty straightforward. Notice in the structure analysis, I'm identifying the machine drill press spot facing tool and then the drill press and the drill bits. Failure mode, the drill breaks. Remember, that's the focus element is the starting point. We say what happens if the drill breaks. That's the failure mode. The failure effect is that the part doesn't have the required hole drilled, then it can't be assembled into the final product. Failure cause, why it happens. Small drill diameter makes the drill easy to break. Breakage usually results from radial forces or excessive torque. That I had to look up. Again, Shigeo Shingo is focusing only on controls to detect the drill breakage. I did some additional research so I could cite failure causes to make this into an example. Severity, 5, part of the production run must be reworked offline. Now, we're not talking about scrap because if there's no drill bit, there's no hole. All they have to do is send it back to have the hole drilled. That's obviously not very good for continuity of operations. Occurrence, there's no prevention controls. Detection, one worker is minding 10 machines, so he or she is unlikely to notice the non-conforming parts. Gives us an action priority of high. Optimization step, verification rods move along with the drill. So when the drill machines the n+1th part, the rods go through the 4 holes in the nth part. In other words, the verification rods move coaxially with the drills as the 4 drill bits are acting on the n+1 part. The n part, the one that has presumably just been drilled, is right next to it, and there's 4 verification rods moving up and down simultaneously with the drill, and those have to go through the part that was just finished, and if they get stopped, obviously there's at least one hole is missing. Then the drill stops and the flashing red light notifies the operator. This is automation or jidoka, in which the machine can detect an abnormal condition and stop itself rather than continue to make non-conforming parts. That's don't make it and don't pass it along. In this case, we've made one non-conforming part, but because the verification rods won't go through it, we're not going to pass it along, and also it's going to tell us something is wrong, so we're not going to make more poor quality. This actually reduces the severity because instead of a lot of parts having this defect, we have only one non-conforming part that must be reworked in station rather than being caught later. So according to the FMEA manual's severity table, that's going to drop the severity from 5 to 3. That's already good. We still don't have prevention controls. The detection rating drops from 9 to 3 because the automation detects the problem in station and prevents it from advancing to the next process. Now this will drop the action priority from high to low, but we still probably want to look into ways to prevent the drill bits from breaking. Now I went a little beyond Shigeo Shingo's example. Shigeo Shingo showed us how to detect the problem if it happens. Now, consider method as a process work element for drilling the 4 holes. I had to do some on-line research about drilling to find out the factors that affect drilling. So if you look at the method, this is drill bit breakage by Union Tool Company. This illustrates how we might expand the process work elements the same way we expand a cause and effect diagram, which is the key takeaway from this slide. I said the process work elements are similar to a cause and effect diagram. Well, we can do the same thing with them as we do with a cause and effect diagram and expand them. So the method includes the chip load, which in turn depends on the spindle speed and feed rate. Friction, if the spindle speed is too slow, that can result in breakage. If the cutting load can cause breakage if the spindle speed is too fast. Well, the nice thing about that is we can put the spindle speed right between them instead of too slow or too fast. We set it just right, and then we can change the feed rate to deliver the correct chip load. So by changing the method, suppose we can optimize the drill spindle speed and feed rate to reduce the chance of drill breakage. This could conceivably reduce the occurrence rating from 10 to 3 due to a technical best practice, which is highly effective in preventing the failure cause. So now we're going to reduce the occurrence rating hopefully from 10 to 3 by making this change. Okay, the last part of this is the control plan. This is from AAAG's APQP manual, Advanced Product Quality Planning and Control Plan, 2nd edition, and also the Stamatis book also discusses control plans. The control plan can apply to a family of products that's manufactured by a common set of process steps, tooling, and activities. And Stamatis says you can get a dynamic control plan by combining an FMEA and control plan using a single form, which makes sense because the control plan can apply to each step of the process and also address the potential failure modes. It's required by IATF 16949. By the way, this is not found in ISO 9001. As I mentioned before, if you're using ISO 9001 2015, I would recommend getting a copy of IATF 16949 because it's essentially ISO 9001 plus additional requirements, some of which, while not required by ISO 9001, are going to be extremely useful and can enhance the effectiveness of your quality system. In any event, ISO 9001 doesn't require control plans. Nonetheless, they're a good idea. IATF 16949 Annex A provides guidance. The APQP manual provides even more extensive extensive documentation, and the Stamatis reference also talks about control plans. And I think I also cited that free downloadable one from Cooper Industries a while ago. Lots of information available about control plans. The control plan layout in the AIAG APQP manual includes multiple fields that are relatively standard in the automotive industry. Fields 1 through 4 are relatively routine. 15, part or process number. 16, process or operation. 17, relevant machine, equipment, tools, and so on. 18, characteristic number. Now, a lot of that is sort of routine now, where I've highlighted the key takeaways. The product characteristic, remember that this relates to detection controls. It's a measurable aspect of the product, such as torque or dimension, that ties in directly with the information of the PFMEA, but it's usually measurable or appraisable only after the fact, which means it's subject to detection controls, which means if it's not right, we'll detect it, but we already have a piece that is rework or scrap. The process characteristic is an aspect of the process that's measurable and or controllable during realization of the product. As I mentioned before, a type of feedback process control endpoint. Detection is an example. Measuring the distance a drill goes into a part while it's being drilled. Those are forms of feedback process control, controllable during realization of the product, and it's subject to prevention controls, which prevents the failure mode from taking place. Stamatis adds the control factor, I listed these before, that supports the process characteristic in terms of being a potential source of noise or variation, which ties in with the FMEA's parameter diagram. Special characteristic class, that often automotive applications. Specification that corresponds to the product or process characteristic, what is to be measured or ensured. Well, in our Shigeo Shingo example, the torque of the bolt that holds the car seat together would be the product characteristic, not the process characteristic. The process characteristic, my understanding is that impact wrenches can be set to deliver a certain torque, so the setting on the impact wrench could conceivably be the process characteristic. Evaluation or measurement, how is the characteristic from column 22 measured or evaluated? That's where we get into gauge calibration and measurement systems analysis, both of which are required by IATF 16949. Calibration has always been required by ISO 9001. Sample size and frequency as might apply to statistical process control. Control method, this is how the product or process feature is to be controlled. Methods include, but are not limited to, automatic process control, which is usually how they do things in the chemical process industry, statistical process control, inspection, error proofing, automation. Basically ask, how do we ensure that the characteristic meets requirements? That's what we ask in context of the control method. The reaction plan is part of the work instruction for the process step. What should the worker do when an out of control or non-conforming situation is discovered? Okay, suppose that automation device, Shigeo Shingo method, Shigeo Shingo mentioned the verification rods for the drilling operation. What is the worker supposed to do if the tool stops and an alarm sounds because the drill bit has broken? That would be an example of a reaction plan. The control plan looks like this. Again, I'm highlighting for the Shigeo Shingo example. bolt installation, the equipment is the torque wrench. The product or deliverable is the torque as a real number measurement. Requirement, it has to be in specification. Measurement evaluation is with the torque wrench, 100% sampling, everyone is checked. The control is that it's checked with the torque wrench. Now the reaction plan is what the worker does if there's a problem. Let's say that the worker checks the bolt with the torque wrench and it's not the correct torque. Well, the next step might be to check the settings on the impact wrench, because I understand impact wrenches can be set for specified torque. So if the impact wrench isn't delivering the correct torque, and notice that was in the previous step, the second line, the process characteristic is the impact wrench torque setting, and it must tighten the bolt to specification. So if that's not happening, then the reaction plan would be to readjust the impact wrench. Okay, summary. The AAAG VDA FMEA handbook, it just came out last year, less than a year ago, I think, contains significant advances over past methodology. Structure and function analysis identify the process factors and work elements, including potential trouble sources. Failure analysis identifies the failure modes and their causes. Remember, the failure cause was formerly the failure mechanism. Failure cause and failure mechanism play the same role in FMEA. And remember, the failure mode is the focus element or starting point, and from that we get the failure effect and also the failure cause. Risk analysis assesses the risks to obtain an action priority rating rather than a risk priority number. That, again, is a major advance on the newest manual that wasn't in the previous manuals. I think the fourth edition FMEA handbook still use risk priority number. Optimization removes or mitigates risk. Key aspects of the failure analysis step. The failure mode is the focus element or starting point. So we go from that to the failure effect, namely the consequences, and also the failure cause. The failure cause is why it happens. The failure effect is what happens. The new approach improves the risk analysis process. Severity covers quality, continuity of operations, and occupational health and safety. A very major advance is the occurrence ratings are now based on the nature of the prevention controls, which we can relatively easily assess rather than probabilities that are often difficult to assess. In some cases, people have to guess at them. Detection ratings based on the detection controls and the action priority is another major advance. Optimization is similar to what was done previously. The FMEA then becomes a quality record whose content can be applied to similar activities, read across replicate or best practice deployment. We saw in that sewing machine example, installation of the machine guard made injuries impossible. That knowledge might have then been deployed to other operations, such as that stamping operation, saying we have to make it impossible for the worker to put a hand into this machine when it's moving. A control plan can be appended to the FMEA to create a dynamic control plan.